We have this standing wave a cos kx cos omega t. Density of the medium is rho. We need to find the energy density, potential energy density, kinetic energy density, and then we need to plot the energy density distribution. So the total energy between displacement nodes. So energy versus x between nodes at t is equal to 0 and t is equal to t by 4. So we are given the equation of the standing wave. We need to find potential energy density and kinetic energy density. So we must know one thing about the solid medium, that velocity is root y by rho. And we know v can be written as omega by k. So this gives the value of y to be rho into omega by k whole square. So we are doing that because when we will write potential energy, we will get a term of y. So we want to get rid of that. So we'll get rid of it in this manner. So let's start. So we know it's given E is equal to a cos kx cos omega t. Notes will be when cos kx is 1 or minus 1. Sorry, cos kx is 0. So that will be when kx is equal to pi by 2, 3 pi by 2, 5 by pi by 2 and so on. Now a part, potential energy density. Now potential energy is due to the elastic nature of the medium. And we know potential energy per unit volume is given by half stress into strain, which can be written as half y into strain square. So as discussed, the value of y we will put from here so that we get the variables which we are familiar with, and strain will be the relative deformation, that will be dou by dou x. So we do dou by dou x of that and we put that value here and put the value of y, we get the potential energy per unit volume to be this. So it varies with x and it varies with time. Now kinetic energy. So kinetic energy we can write as half dm into d kinetic energy. So small kinetic energy is half dm into vx square. So at a given x, this is the kinetic energy. dm can be written as rho dv and vx is dou by dou t. So we'll again put dou by dou t from here, and this dv will take to the left side so that we get the kinetic energy density. So that comes to be half rho dou by dou t whole square. So if you do dou by dou t and put here, we get this as the answer. So these two are the variation of potential energy and kinetic energy densities as a function of x and time. So if we just add these two, we will get d by dv, that will be dpe by dv plus dke by dv. So why we are adding them? Because that we need in the third part where we need to plot the total energy density. The total energy density is adding these two. Now at t is equal to 0 and t is equal to t by 4. So at t is equal to 0, this term will be 1 and this term will be 0. So the energy density at t is equal to 0 is half rho a square omega square sine square kx, or you can say some constant times sine square kx at t is equal to 0. At t is equal to t by 4, cos omega t will be 0. So this term will be 0 and this term will be 1. So energy density at time t by 4 will be the same constant times cos square kx. So now we can plot that between the nodes. So nodes will be, let's say at x is equal to pi by 2k and then x is equal to 3 pi by 2k. So let's take these points. So x is equal to pi by 2k is a node, x is equal to 3 pi by 2k is also a node. So in between them, let's plot these graphs. So sine square kx. So when you put pi by 2k here, this term will become 1. So it reaches its maxima here, d by dv. Then it will reduce to 0. And finally at 3 pi by 2k, if you put that value in x, this will again become 1. So it will go from c to c. And at t by 4, at x is equal to pi by 2, this term will, not x is equal to pi by 2, sorry, x is equal to pi by 2k. So at x is equal to pi by 2k, this term will become 0. So it will start at 0. And then it will reach its maxima and then it will go down. So this is the plot of d by dv versus x at t is equal to 0 in blue and at t is equal to t by 4 in red. Now he has not asked, but let's also plot E at these two instants. So at t is equal to 0 and t is equal to t by 4. So at t is equal to 0, if you put here, so this will be 1. So again, if you put x equal to pi by 2k, so it will start at 0. Then it will reach the maxima, and then again it will become 0 at 3 pi by 2. So the variation of E will be like this at t is equal to 0. At t is equal to t by 4, cos omega t will be 0. So E is always 0. So all the particles are crossing the mean position at t is equal to t by 4, and at t is equal to 0, all the points are at their maxima in this standing wave. So now you can see the relation between the energy variation and the position of the particle. So here, when all the points are at maximum, here the energy density is 0. Sorry, here at the node energy density is maximum, and here at the antinode energy density is 0. So in a standing wave at the antinodes energy density is 0, because the kinetic energy of the particle is also 0, and the string is not stretched, that we saw in the previous problem also, that at the antinodes the string is loose, it's relaxed. So potential energy is also 0, kinetic energy is also 0, so total energy is also 0. And at node, the kinetic energy is 0, but potential energy is maximum, that's causing the peak here. Same here also. Now when all the particles are crossing the mean position, that time at the node the string is relaxed, and because its kinetic energy is also 0, so total energy is also 0. The particle which is crossing the mean position is crossing it with maximum kinetic energy. So the string is still relaxed, but at this moment all the particles have maximum kinetic energy. Because of that, the total energy is at peak. So here the kinetic energy is 0, but all the particles have maximum potential energy. And here the potential energy is 0 and all the particles have maximum kinetic energy. However, these points can never have any kinetic energy, and these points can never have any potential energy. So you can see all these graphs and compare it with, I think you need to take a very good look at how the energy is variation, and even kinetic energy and potential energy variation happens between the two nodes in case of a standing wave. So make sure you understand all these correlations pretty clear, and then move on. All right.